Okay, this PowerPoint and presentation is going to cover a lot about stoichiometry. It's going to cover the basics, limiting reactant, excess reactant, how to break down a representative particle, density, molarity, all things that can be used in conversions. So let's start with the basics. At the very heart of chemistry is the mole. Okay, you use the mole to get between all different types of units. Now, the mole can be converted to multiple different units. The first one that I'm going to talk about is if you wanted to convert to liters. Now, if you wanted to convert to liters, the way you get there is by using the number 22.4. 22.4 liters are equal to 1 mole. Now, there is a special caveat about this conversion. The 22.4 liters being equal to a mole is only true when it is a gas at STP. For those who do not remember, STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius and 1 atm. Now, if you wanted to get to liters, and it wasn't a gas, and it wasn't at STP, you have other options. One of the other options is to use molarity. Molarity, which we will go into more details later, is moles over liters. So it's a conversion that allows you to go from the mole at the heart of everything to the liter if you aren't at standard temperature and pressure. The other unit you may want to convert to is the gram. To get to grams, if you're in moles, you're going to use molar mass. We've talked about molar mass in a previous presentation. It is the number of grams that you total off the periodic table. That is going to be equal to 1 mole. Now, if you wanted to get from the gram straight to the liter, you could use density. Density is equal to mass, which could be in grams, kilograms, whatever, but it allows you to convert from mass to volume because density is mass over volume. And I'll talk about that more in detail as we go on as well. The last branch that you might be converting to is what we call a representative particle. Now, this is the hardest branch for students to learn. There are 3 representative particles. The first one is the atom. That is the representative particle for an element. The second representative particle is the formula unit. The formula unit is the representative particle for an ionic compound. Recall, in a previous presentation I told you that an ionic compound is made up of a metal and a nonmetal, or it may have a polyatomic in place of one of those. The third unit is the molecule. The molecule is the representative particle for a covalent compound, and covalent compounds are made up entirely of all nonmetals. What representative particle you use depends on what type of compound or element is mentioned in the problem, so make sure you pay attention as we go over them. Now, to convert to one of these 3, atoms, formula units, or molecules, you're going to use Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. That is the number of representative particles, whether it's the atom, formula unit, or molecule, that is equal to 1 mole. So here's an example of a question that you might receive. How many grams of oxygen are in 20.2 grams of acetate? Now, when you read a question, you always need to know what you've been given, 20.2 grams of acetate, and what you want, grams of oxygen. Start with the given, 20.2 grams acetate. And yes, you have to know what acetate is. That's why I gave you the list to memorize. Acetate is C2H3O2-. Now, you're converting between grams and grams. And the first thing you might say is, what? How? Well, the first thing you know is to get to the heart of everything. Okay, the heart of everything in chemistry is the mole. So the first thing to convert to is the mole. To get from grams to the mole, if you look at the chart, you use molar mass. Follow the units. Since grams are on the top, grams have to go on the bottom of the next conversion. Total up the molar mass of acetate. Carbon is 12 on the periodic table. There are 2 of them, so it's 24. Hydrogen, 3. Oxygen, 16 times 2 is 32. Total it up and you get 59.0 grams for every mole of acetate. But the question does not concern itself with acetate, it concerns itself with oxygen. So when you look at 1 mole of acetate, you need to figure out how many moles of oxygen are in 1 mole of acetate. And when you look at acetate, there are 2 moles of oxygen. Lastly, you want to go to grams. So to get from the mole back to grams, you use molar mass. Molar mass of oxygen is 16.0 grams. Total it out on your calculator, you get 11.0 grams of acetate. Now in terms of sig figs, why 11.0? The number of sig figs in your answer is going to be the same as the number you started with when you convert. Since this has 3 sig figs, this has 3 sig figs. Now, this is the meat of this. If you can understand how to break down a representative particle, you'll be doing much better off than your peers this year. The 3 representative particles were the atoms, the formula units, and the molecules. Those are your 3 representative particles. Now remember, formula units are for ionic, molecules are for covalent, atoms are for elements. Okay? So when you get something, like let's say magnesium, and I want to say 1 mole is equal to 6.02 times 10 to the 23rd what? Your job is to decide what magnesium is classified as. Is it an element, an ionic compound, or a covalent compound? Since magnesium is an element, 1 mole of magnesium is equal to 6.02 times 10 to the 23rd atoms. The reason this is so is because the smallest piece that magnesium can be broken down into without changing its properties is the atom. On the other hand, what if I gave you water? Okay, and I said 1 mole of water is equal to 6.02 times 10 to the 23rd what? Well, water is not an element. Water is made up of hydrogen and oxygen. They're both nonmetals, so it's covalent. It's equal to 6.02 times 10 to the 23rd molecules. The reason it's not atoms is the smallest piece you can break water into without changing the properties of water is the molecule. If you broke it down into a hydrogen atom, then it would be explosive versus the fact that water is not. So you can't change the properties when you're defining a representative particle. That's why the molecule is the smallest piece of water without a change of properties. But that's not to say the molecule can't be broken down, okay? A molecule can be broken down into atoms. It's true. There are hydrogen atoms and oxygen atoms in the compound of water, but it doesn't include Avogadro's number. When you look at 1 molecule of water, the question is how many atoms are there? Well, you have 2 hydrogens and 1 oxygen, so there are 3 atoms in a molecule of water. The last one is NaCl, that I'm going to give you an example. NaCl is ionic. So when you say that 1 mole is equal to 6.02 times 10 to the 23rd what? The word that you must fill in is formula units. Now that's again not to say that it can't be broken down further. A formula unit can be broken down into ions. Ions are defined as charged particles. There are 2 parts to an ionic compound, the positive and the negative. How many positives are there? How many NAs? There's 1 Na. How many Cl's are there? 1. That means that in the compound of NaCl, there are 2 ions. So, in an example problem like this, how many atoms are in 4.7 liters of methane gas at STP? Start with your given, go to what you need. 4.7 liters of methane. Now you do have to know what methane is. I expect every one of you to know that methane is CH4. 4.7 liters of methane. First, get to the mole. It's at the heart of everything. Since it's at STP, I can use 22.4 liters. Now, I know I'm going to that representative side of the heart chart that I showed you on the first slide of this presentation, but I'm not sure if I can go directly to the atom or not. I know that a mole goes on down here, and I know I've got something to do with Avogadro's number, 6.02 times 10 to the 23rd. But the question is, what? Atoms, molecules, or formula units? Now, CH4 is covalently bonded. It's got all nonmetals. So the word you fill in is the molecule. It doesn't matter if you want atoms. You can't just fill in atoms. You have to fill in the appropriate term. Your job is to take it a step further and go from the molecule to atoms. So when you look at a molecule of CH4, how many atoms do you see? 1 C, 4 H's, that means there's 5 atoms. Run it through your calculator, paying attention to significant figures, and I end up with 6.3 times 10 to the 23rd atoms. Here's another question as an example. How many ions are in 2.34 grams of magnesium sulfate? So I'm going from grams of magnesium sulfate to ions. The fact that it even asks for ions tells me right off the bat that I'm going to be breaking down formula units, because the only 3 representative particles are the atom, the formula unit, and the molecule. I know ions aren't a representative particle. I know I'm going to have to break down the formula unit. So start with the 2.34 grams of magnesium sulfate. And yes, you have to know what magnesium sulfate is. Since magnesium has a charge of 2 plus and sulfate has a charge of 2 minus, it's just MgSO4. Get to the heart of everything, the mole, by using the molar mass. Total up the molar mass of magnesium sulfate. Magnesium is 24.3, sulfur is 32.1, 4 oxygens is 64. Total it up and you end up with 120.4 grams of magnesium sulfate for every mole. Then 1 mole of magnesium sulfate. Now comes the time to use that Avogadro's number. Just make sure you use it appropriately. Since magnesium sulfate is ionic, well, how do I know that? It has a polyatomic ion in it. It's a dead giveaway. The representative particle is the formula unit. But I don't want formula units. I want ions. So in 1 formula unit of magnesium sulfate, we need to figure out how many ions there are. When you look at magnesium sulfate, the magnesium is the positive side, the sulfate is the negative side. How many magnesiums are there? Not its charge. How many magnesiums are there? There are 1. How many sulfates are there? There's 1. Therefore, there are 2 ions in 1 formula unit of magnesium sulfate. Run it through your calculator, pay attention to significant figures, and you get 2.34 times 10 to the 22nd ions. Now, a little more complicated is when you are given a chemical reaction. It's still the same process though. Figure out what you have and what you need. But when I see a balanced chemical reaction, I label all my givens and unknowns under the chemical species in the balanced chemical reaction so that I never have to read the question again. I want to summarize it all the first time I read it. That way I don't have to keep rereading the question because I forget where I'm going. So it says right off the bat, I have 4.3 grams of magnesium. So under magnesium, I write 4.3 grams. We're added to a reaction vessel with ethanoic acid. So that tells me this thing is ethanoic acid. How many moles of hydrogen are formed? So under hydrogen, I'm going to go, I need to know how many moles of hydrogen I have. Start with your given. You were given 4.3 grams of magnesium. Get to the mole. 1 mole of magnesium by using molar mass. The molar mass of magnesium on the periodic table is 24.3 grams. Then mole ratio. A mole of magnesium, if you look here, there's a 1, coefficient of 1, to the hydrogen, 1 mole of hydrogen. Now, do I need to go further or not? The question asks for moles of hydrogen. Since I'm in moles of hydrogen, I'm going to stop. Plug it through on my calculator, and I get 0.18 moles of hydrogen. Now the next one looks pretty much the same. Same chemical reaction, asking for moles of hydrogen, but I know as soon as I label this problem, it is not the same. I have 3 grams of magnesium, I have 12 grams of ethanoic acid, and I want to know how many moles of hydrogen are formed. Now, for my students, when I taught you guys these types of problems, I said when you see 2 numbers on the left of the reaction, meaning on the reactant side, something in your head has to go off. This means if you are given 2 given numbers for reactants, it means that you have a limiting reactant problem. That means that one of those reactants is going to run out, and it's going to limit how much product you can make. Just like when you make s'mores. If I give you a box of graham crackers, or a case of chocolate, and only 1 marshmallow, you can only make 1 s'more. It doesn't matter that you have a wealth of other ingredients. The one that you have that produces the least product is what we call the limiting reactant. Whenever you do a limiting reactant problem, it's unfortunate because you have to do 2 grids. Start with both numbers. I'm going to start one grid with 3 grams of magnesium, and I'm going to start the other grid with 12 grams of ethanoic acid. First, convert them both to moles. 24.3 grams of magnesium, 1 mole of magnesium. For every 1 mole of magnesium, I have 1 mole of hydrogen. Stop there, get my answer. 0.12 moles of hydrogen. Do it for the other one. 12 grams of ethanoic acid. Total up the molar mass of ethanoic acid, and I get 60 grams for every mole. For every mole of ethanoic acid, for every 2 moles of ethanoic acid, I get 1 mole of hydrogen. Run it through on my calculator, and I end up getting 0.100 moles of hydrogen. So the question is, great, but now I have 2 answers. So which one is the number of moles of hydrogen? Because this number is smaller than the previous answer, this is the amount of moles of hydrogen you can produce. And because this reactant produced the least amount of product, that means that the ethanoic acid was the limiting reactant, which by default makes the magnesium the excess reactant. So keep that in mind because we're about to figure out how much excess would be left over. So you know magnesium is going to be left over, but you don't know how much. The key is the difference between what you thought you would get and what you potentially could have gotten. So between these 2 numbers, we need to figure out how much magnesium would be left over. So when you want to figure out how much excess is left over, subtract the answers from your 2 grids. So the 2 grid responses was that you had 0.12 moles of hydrogen, and the other one was that you had 0.100 moles of hydrogen. When you subtract those, and with sig figs, you get 0.02 moles of hydrogen. That's the difference. However much magnesium would have produced this much hydrogen is how much is going to be left over. So what you need to do now is convert this number back to the units of the excess reactant. So convert back to the units of the excess reactant. So what was the excess reactant? It was magnesium. Magnesium was given in the problem in grams. So your job is to convert the 0.02 moles of hydrogen back to grams of magnesium. So first do your mole ratio and then get back to grams. For every mole of magnesium, you have 24.3 grams of magnesium. Run it through on your calculator and you get 0.5 grams of magnesium, and you're done. So just to go over the terminology, the limiting reactant is the reactant that runs out first, so it produces the least amount of product. The excess reactant is the one that's left over once you complete a reaction. All limiting reactant problems require 2 grids, and you're going to know it's a limiting reactant problem because you're given 2 amounts of 2 reactants. Now, molarity. Molarity is defined as the moles of solute over the liters of solution. Now we need to talk in detail about what those terms mean. Solute means the substance that was dissolved. So whatever was dissolved in the question, that substance needs to be converted to moles and put on the top of the molarity equation. In Kool-Aid, what do you dissolve? It's the powder. The powder is the solute. The solvent is the substance that did the dissolving. A lot of times it's water, and in Kool-Aid it happens to be water too. You may have heard the phrase, water is the universal solvent, and you will hear me say it as well. The solution is defined as a combination of the solute and the solvent. So when you put together powder and water, what do you make? Kool-Aid. The Kool-Aid, however much volume of Kool-Aid you make, that goes in the bottom of the molarity equation. Once you divide the moles of the stuff that was dissolved by the liters of how much Kool-Aid you made, you'll have the molarity of the Kool-Aid. A solution is also known as a homogeneous mixture. Since it's a homogeneous mixture, it's made up of multiple substances and that are evenly distributed. There is no distinguishment of phases. There's no separate powder from water in Kool-Aid. Now, the thing to take to note here is that molarity is a conversion between moles and liters. So when you can't use 22.4 liters equals 1 mole, you can use molarity to get between moles and liters. Now, same technique, label, label, label. 25.0 milliliters of NaOH, and it's 0.4 capital M, which means molarity, was added to an excess solution of oxalic acid. Now I write excess as XCS. That basically tells me this is the excess reactant. The sodium hydroxide is the limiting reactant, so I don't have to do 2 grids. But I do need to figure out how many grams of sodium oxalate were formed. Now, remember, molarity is 0.4 moles of solute per liter. So 0.4 moles per implies 1 liter. So take the molarity and break it down into a conversion that you can use. When you go to do your conversions, never start with molarity. It's a conversion. You use it later. That means you start with the 25 milliliters of sodium hydroxide. Now, you can't use 22.4. It's not a gas. It's not at STP. So you need to get to the point where you can use molarity. Well, molarity is in liters. Your current number is in milliliters. So the first thing to do is to get out of milliliters and go to liters. I covered how to do this in one of the first videos of your summer work. Now that you have a liter, you can flip this 0.4 moles per liter any way you want to fit it into your conversion. So you can say there are 0.4 moles per liter, or you can say per liter there are 0.4 moles. Now if you look at your grid, right now liters are on the top. You want liters to go on the bottom. So you're going to say 1 liter is 0.4 moles. That's the way it works for you. Now that's 0.4 moles of sodium hydroxide. You want sodium oxalate, so you do a little conversion. There are 2 moles of sodium hydroxide for every 1 mole of sodium oxalate. But that's not enough because of course they don't want moles, they want grams, so they're making your life a little harder. For every mole of sodium oxalate that you have, total up the moles and you get, the grams, and you get 134. Run all of this through your calculator and you get 0.670 grams of sodium oxalate. And you're done. So that's just to show you, you can take molarity and you can put it into a grid to accomplish your purposes. Now, density. Density is also a conversion. Density is a conversion, though, between mass and volume instead of moles and volume. Like molarity, it's a way you can get to using volume without using 22.4. So how many grams of water can be produced in the combustion of 50 milliliters of isopropyl alcohol? The density of isopropyl alcohol, C3H8O, is 0.786 grams per milliliter. So I want to know how many grams of water, but I have 50 milliliters of isopropyl alcohol and the density of isopropyl alcohol. Well, I'm going to need a balanced chemical equation, and I notice it mentions combustion of isopropyl alcohol. So take the isopropyl alcohol, combust it, which means react with oxygen. You should know from your previous videos that you're going to make carbon dioxide and water. Then balance it. I'm not going to spend the time on the balancing, but the coefficients end up being 2, 9, 6, and 8. Now I'm going to summarize what I have. I want to know how many grams of water, and I have 50 milliliters of isopropyl alcohol with a density of 0.786 grams per milliliter. Now, just like I told you earlier, don't use molarity as your starting number. It's a conversion. You use it later. The same thing is true of density. So don't start with the density, use it later. That means you got to start with the 50 milliliters of the C3H8O. Now, density is in grams per milliliter, so I can use that. I can say there are 0.786 grams per, means 1 milliliter, or I can say per milliliter there are 0.786 grams. According to the units here, I need milliliters to go down, so I'm going to use the first version of that conversion. So 0.786 grams per 1 milliliter. That's the grams of C3H8O. I got to get to moles. To get to moles from grams, I use molar mass. The molar mass of C3H8O happens to be 60 grams per mole. Then you do your mole ratio. If you look at the balanced chemical reaction, there are 2 moles of C3H8O for every 8 moles of water. For every mole of water, there are 18 grams. Total it out in your calculator and you get 29.5 grams water. And you're done. Finish your quizzes and I will see you soon.